In 3D graphics, as well as in reality, we can distinguish light sources based on some of their features, which are basically the following: the size of the light emission area, and thus the type of shadow created. Point lights can be assimilated to a light with an infinitely small emission area, such as a hypothetical point. A point light is identified by its ability to cast extremely sharp shadows. Remember that the smaller the surface of the light, the sharper the shadows are. Furthermore, the generated shadows follow the perspective of the point of emission. Sunlight is essentially a point light, but it has the property of producing rays that are parallel to each other, just like a very distant light source. The generated shadows are parallel and not projected prospectively as with a point light. As a result, we will use this light whenever we need to simulate the illumination of the sun. Once again, the generated shadows are extremely sharp. The spotlight is like a point light, but behaves by simulating a conical reflector with a directional beam of illumination. As we've seen, the problem with these light sources is that they cast very sharp shadows, just like very small real lights. To solve this problem, another type of light has been introduced, the area light. This light has an emission surface that can be increased or decreased as we want. In this case, the light rays come from an entire surface. As a result, the shadows are softer and proportional to the size of the light surface, as we expect to be with real lights. But these lights also have an issue, which is the noise they have in the shadows area. To reduce it, you must greatly increase the sampling rate, which significantly slows down the rendering time. In a real scene, the illumination of objects is determined by each individual ray of light that starts from the light source. This would be impossible in computer graphics, because it would require tracing the path of trillions of light rays. However, only a fraction of the rays in a scene reach the eye or the camera. In ray tracing, therefore, the opposite approach is taken. The light rays are computed from the camera's point of view. This drastically reduces the number of calculations, while maintaining a high level of accuracy in the lighting calculation. Ray tracing, combined with standard light sources, yields satisfactory but not completely photorealistic results. In reality, the light rays bounce and spread in all directions, with the result of partially illuminating even areas in shadow. Furthermore, the light is colored according to the type of surface on which it is reflected, assuming different colors, depending on the coloration of the objects in the scene. Let's take a look at a rendering that does not take these factors into account. You can notice that the shaded areas are completely dark, and there is no mutual influence between the objects in the scene. Here's what happens when we consider diffuse light, or light that is also reflected by the atmosphere and the environment. The areas in shadow are lighter, and they also have a slight blue tint, which is exactly the color of the environment. Here we can see the effect of light reflecting from surrounding objects. As a result of the indirect light, the sphere and the floor have a red coloration at their closest points to the cube. Finally, here is the combined effect of diffuse light from the environment and reflected light from objects. These lighting algorithms are called global illumination and final gather. The rays of light that reflect on the surfaces in the scene are computed using global illumination, resulting in indirect lighting even in the shadow areas. Let's start from a scene with a planar light source. Thanks to global illumination, the addition of a colored atmosphere changes the brightness and coloration of objects. If we add a white panel on the side, it will lighten the shadow areas because it reflects some of the light, just as it does in reality. On the other hand, in Final Gather, the brightness and color of the image are calculated based on the color of the pixels of the objects themselves, rather than the light rays of a light source. Each point, therefore, is influenced by the surrounding pixels, according to their color. Here you can see how the floor is colored like the panel and the cube. In Final Gather, the light of the scene is calculated using the brightness and coloration values of the objects in the set. As a result, two nearby objects influence each other's brightness and color. And this adds realism to the scene. A surprising application of this is the use of images to light a scene. The brightness values of the pixels in the image, in fact, behave as if they were light dots. As a result, the image becomes a single source of light based on the brightness and coloration of its pixels. The most common use is to illuminate a 3D scene with HDR images. As a result, the scene is lighted exactly as if it were placed in the original environment. To better understand how this works, consider lighting the set with a sequence of images similar to this. This is an animation in which a series of graphic elements appear one after the other. Simple white stripes, and then circles, which then become colored. If we use this image sequence as a lighting map, the scene will be lit, as if each graphic element were a real light. If the color of the image light areas changes, so will the lighting of the set. Finally, here's what happens when an HDR image is used as a light source. The sphere is illuminated as if it were a part of the photographed landscape.